Hi, thank you for having me. My name is Matt Johnson-Roberson, and I'm a professor at Carnegie Mellon's Robotics Institute. Today, I want to talk to you about a few different projects we have kind of ongoing that are related to learning as associated with, in this case, self-driving cars. But I really think it translates to a bunch of different domains beyond just self-driving and thinking about how robot learning can be applied more broadly. So, why self-driving? I think it's been this strong motivator for a long period of time. And one of the things I like to stress when I talk about self-driving is I think you always need to put in perspective that this is a problem that we've been thinking about in robotics in the world for quite a number of years. And so, this is an image of people happily playing in the back of their car and not having to drive. And, that's such a strong motivator for people in thinking about the way that they would like to see the world and how we like to use our time that I think it's been interesting that people have been working on this for as long as they have. I like to go back historically to look at one of these early projects. This is an RCA project from the 1950s where you have cars that were built to work with the infrastructure built into the roads. And so this vehicle controlled position using metal cables embedded in the asphalt. And then the drivers here controlled the throttle. But, again, to stress, this is really a very early approach, but it's worth highlighting that, there have been numerous approaches. And so, when we think about the modern context and all the money and energy that's going into self-driving, there have been just a number of projects that have backed that up. So here you can see, I like to think about this sort of on the kind of historical arc. And from the 1960s till now, or to the sort of modern era, right, we just see this real advancement in, I guess, both number of sensors, complexity of those sensors, the ability for sensing modalities to produce high fidelity models of the world. And obviously, computing power is also increasing in that same period of time. But really, one of the things that this sort of points out is a lot of these advances we think of in sort of a vacuum when it comes to learning technologies that have advanced in the same period of time. And so obviously machine learning has advanced significantly in this same period of time. And so one of the things is perhaps going back and reassessing some of those assumptions that have been made about how to design these vehicles and what they need to do to figure out where we need to go. So I like to think about sort of one of the biggest challenges that we face, and that really is around the differences between what pure vision has had and other aspects of machine learning that aren't robotically related, and what we've seen in sort of the self-driving world, right? And so there is a real difference between solving some of these vision problems that exist in sort of the abstract, for big search engines, or in the case of ImageNet, obviously classifying images without further context. But again, thinking about robots that are moving around in the world, there's a very different set of problems there. And I think one of the important things is always to keep in mind the challenges that we face in robotics when thinking about the fact that, even if you produce closed world data sets that are pretty comprehensive, you are really learning in a vacuum relative to what real robots are going to experience when they go out there and are deployed. Right. So there's this contrast, right? If we think about, computer vision and things like ImageNet, and then we think about robot vision, we think about these big data sets that have been produced by companies and universities, right? There is a real contrast. There's a real challenge. And I would say that both of these in some ways are insufficient, right, for us to really move forward. And so, we need to think about the limitations of the fact that these labeled data sets came at great expense and are really, really hard to produce. And sort of their inflexibility is one of the bigger challenges I think we face moving forward, and how do we think about where this is going to go and what it's going to do. Okay, so we're clear we're talking about robots. We're not talking about just this generic labeling problem, right? And I'll stress kind of three things that I think are important when it comes to thinking about, directions that, people that I've worked with and my students and postdocs have undertaken, but also more importantly, what I think is important for, the intersection of learning and robotics, right? So how do we escape this problem of having to continuously label large amounts of data to really understand, benchmark, and know how we're doing, or even learn in the first case, right? So the three things that I think I always come back to in robotics that I think are critical are these three right here. So self-supervision and unsupervised learning. Obviously, this goes beyond just robotics. This is a huge topic lots of people are looking at in lots of areas in machine learning, not just for robotics, but I do think it is one of the keys to thinking about what we can do in robotics. And the idea of self-supervision actually has a lot of value, I think, when you think about a moving platform, because there are a lot of consistencies that come from the physics of the world that you can use to enforce things like self-supervision. And so that leads us into the second one, physics, right? And because robots are operating in the physical world, there are a number of things that, you know, create constraints, create a set of properties that allow us to track things over time, to look at how things move, where they go, all those kind of things. And then finally, simulation, right? And we've seen a ton of work on this. Obviously, the sim to real problem is one of the most dominant issues when it comes to thinking about this. But I think that there's a lot of work to be done in simulation. And certainly our group and others have looked at a lot at photorealistic simulation. But I think one of the things that's becoming clearer is that there's sort of a lot of ways to use simulation beyond just sort of the video game style engine or really photorealistic visual simulator. I think we need to think about simulation in other ways as we kind of begin to scale up and think about these large scale machine learning problems. Okay, this first set of work I'm going to talk to is from a postdoc currently at UMich, who is a former PhD student of Ron David and myself, named Mani, who again is based in Michigan currently. So he did this work in the context of the Ford Center for Autonomous Vehicles, where I was prior to coming to CMU, and they've been really thinking a lot about adverse weather conditions and how that intersects with robotics. So they built this sensor rig. It has a LiDAR. It has RTK GPS. It has conventional RGB cameras. And then it also has two novel sensors, or more novel sensors, I guess. It has a cooled thermal camera, which you may not be familiar with, but cooled thermal cameras are typically used for very high precision, very calibrated thermal measurements. So they're used a lot in surveying and in other techniques, but we don't really see them deployed in robotics primarily because of their expense. And the reason they're called cooled is they rely on cooling down the imaging sensor to a point where a lot of the noise that you would normally see in thermal cameras is reduced. And then finally, we have some uncooled thermal cameras, which are much closer to what you're seeing deployed on in automotive context now, that are used for everything from people detection to other things. But again, one of the things that we think is interesting is, okay, well, what can we do when thinking about ways of using these novel sensors to do interesting work in the self-driving context using learning? So when thinking about adverse weather, this work was done in Michigan, which has a lot of adverse weather. And one of the interesting things is that we believe that thermal cameras kind of unlock some of the challenges associated with typical RGB cameras or LiDAR in these adverse weather conditions. And so what you're going to see here is the vehicle moving. You can see that there's a thermal image with a fair bit of noise in the upper right. You can see another thermal image in the lower right. That is from the cooled camera. And then in the lower left, you can see another kind of higher noise thermal image. And you can kind of match that all with the video imagery. But you can see that, as this vehicle moves around, particularly in conditions where there's snow, you end up with lots of noise in the LiDAR point cloud. And in some cases, even in the RGB imagery. And so we think that this is one of the fundamental challenges, right? When you think about scaling up self-driving cars to many, many contexts, right? The noise associated with a lot of these adverse weather conditions really does preclude lots of the stuff you'd want to normally do in a sensing environment. So you can begin to see the snowflakes kind of coming through, even in the thermal imagery. Right. So, when talking about these two different types of cameras, right? Well, first we have this FLIR, which is sort of this A655, which is sort of this mid-range thermal camera. We have another uncooled camera, the FLIR 80K, which is the 3K camera. And the challenges with these sensors is really that noise profile that we were talking about. And the cooled camera doesn't have these, but that cooled camera is hundreds of thousands of dollars. These cameras also have rolling shutter, and there's not a ton of data sets out there. And even the kind of really expensive ones, expensive sensors, don't really have a lot of data associated with them. So here's another example. This is another kind of condition that you'd have to deal with when thinking about, uh, autonomous driving. This is going to be a tunnel where they produced a ton of smoke and then are looking at the effect of that on these sensing modalities. And again, one of the goals is smoke or fog, right? Is another thing that would obscure your sensors. And as they kind of increase the density of that, you can see that, particularly in the cooled thermal camera, you can really see through that in a way that you wouldn't be able to in the RGB context. Right. So the question is, okay, how do we perform this kind of imaging and get dense ground truth in adverse lighting and weather conditions, right? So there's been some other approaches that have been put out there to attempt this. Probably most common in the literature are beam splitters that take in light from two different, or from a single source and then split it into two different types of cameras. So that can be to your, thermal camera and your RGB camera. Now you have pixel perfect alignment of these two types of images, which is super useful if you want to do comparisons of two different types of cameras or two different modalities, etc. The challenge here is that this tends to be a bulky setup. It's hard to deploy in the field, and it needs radiometric calibration, which again can be kind of costly and expensive, right? And it's also very difficult to weatherproof, and the synchronization sort of challenges of that are significant. So, one way you can try to address this that's not beam splitters is trying to use depth maps or depth information to project from two calibrated camera viewpoints, right? So in this context, what we're going to see is trying to do that with, a sparse LiDAR point cloud. And one of the things that should become apparent is that you can see the point cloud over there on the right? You don't have dense depth information for every pixel. And as a consequence of that, right, reprojecting using just that information is actually really, really difficult, right? And so, you can use learning algorithms to attempt to fill in gaps. You can do other things where you try to, use the imagery to regularize what you're seeing. But the fundamental challenge is that there's always going to be a fair bit of noise in that reprojection, given the fact that you don't have dense pixels for every point. And then more importantly, that there are visibility constraints that exist in the LiDAR point cloud, or in the 2D imagery that don't exist in the LiDAR point cloud. You can see through things are obscured, vice versa, which obviously makes it very difficult to use that information to reproject. Okay, so there's been a ton of work, as I'm sure everyone here is already aware, on using NeRFs, right, neural radiance fields, to generate novel views, right? So, these are sort of canonical examples of that, but you have your multiple pictures and you can generate novel viewpoints there of the car, or over here of this table, right? And associated depth maps. So that's been very, very powerful. And if you think about what the primary application of NeRFs have been, right, is for novel viewpoint rendering, right? That's sort of one of the biggest areas of success that field has had. One of the big differences that we have with this work, though, is that we have very sparse data from our, for our NeRF to train on. So you can see there in image 1 and in image 3, that image has translated so much that mailbox is no longer visible. So this is obviously a really, really big problem, and just using NeRFs on this level of sparse imagery tends to have pretty poor performance, right? So this is a NeRF trained on just those two images, and you can see that trying to render a novel viewpoint there doesn't do very well. Great. So, to address this challenge, Mani and his colleagues have been working on figuring out ways of using the projected LiDAR scans to produce per pixel depth information, and then from that per pixel depth information, compute dense optical flow, and then use that flow information to sort of address the sparsity issues we have with the number of images when trying to produce a NeRF, right? So again, we have the sparsity of views. That's one of the big challenges. There's noisy images from thermal cameras, right? And that violates things like the brightness consistency constraint or multi-view consistency. And then we're doing the sampling for a large scene. So, to address the sparsity of views, he's using the LiDAR. To address the noisy image, he separates the MLPs for sigma and for color. And then to sample a large scene, he's using occupancy grid mapping on the GPU. Great, so let's have a look at the results. right? So there we have a house, a parking structure, a parking lot, a tree, and just a street scene. So you can see some of the results. You can see the rendered image there in the center, which again has a sort of highly denoised version of what we saw before. You can see that, again, there's challenges with the background. Obviously, they're off in infinity, but if you look at the objects in the foreground, you can see quite a bit of noise reduction from the original. And then you see the same here, producing one from the road scene. And then finally, here's us rotating around a tree, and you can see again that they're able to do a reasonably good job. And one of the other interesting dynamics of this, right, is you can see that sort of this implicitly denoises the images. So you can see a ground truth image there on the left, and then the one rendered from NeRF there on the right. And you can see that there's an implicit, reduction of that salt and pepper noise you can see across the image, right? And that's sort of the clipped absolute value of the differences between the two. It also serves as an implicit denoising of the point clouds for the production of these NeRFs. So you can see the aggregated LiDAR scans there. You can see then that rendered by InfraNeRF, which does a good job of interpolating between those sparse LiDAR points. Right. So, what was the purpose of all this? Well, we're trying to be able to render images from the microbolometers pose. And so you can see that's the raw microbolometer data, a fair bit of noise, a fair bit of motion blur. And then you can see the rendered NeRF image there over there on the right. This also allows us to do things like render depth and render flow, which again helps us if we're thinking about what we can do with these data sets. One of the other interesting aspects here is you could render hypothetical novel cameras that don't exist or that you don't have in your data set. So there's microbolometer data, the wider field of view microbolometer, and then you can see the same thing there rendered by the NeRF, right? So we're rendering a much larger field of view than we have in the other image, again, which allows us to kind of generate novel data to be able to play around with. And then you can see there's the wider field of view depth map and wider field of view flow. So the hope is with this approach that you could use one cooled camera to many microbolometers and generate a variety of different lenses, different positions, different resolutions, different frame rates, etc. Okay, switching gears, we're going to talk about some other work, learning-based work. This is from Cyrus Anderson. He's a graduate PhD student here from University of Michigan. And so, one of the things that has sort of been a huge aspect, obviously, of autonomous driving, and one of the big limitations that we've seen to date, right, is that the fact that these vehicles struggle to interact with other cars, right? So here's an example of somebody trying to, or watching a Waymo vehicle trying to merge and missing multiple opportunities and then having to get off at the exit because it was incapable of merging. Right. We also see these kind of big emergent behaviors when we think about large groups of pedestrians and cars and how they're able to kind of navigate these things. But again, thinking about what an AV would do in that situation is obviously really, really difficult. So if we want to make predictions about pedestrians or other vehicles, right, there's a bunch of approaches that people have taken historically. We can look at things like taking that data as a time series and Kalman filtering it, or using things like RMAX. The challenge with that is typically very difficult to incorporate semantic information or social data. So how do these different things interact with each other? There's been a lot of work around inverse optimal control, fixed goals, switching goals, etc. Challenges with that is it doesn't typically scale to the number of pedestrians. And then there's been a bunch of approaches, obviously, in the learning realm in the last couple of years. And so we see a lot of deep neural net approaches, everything from social GAN, which uses global pooling, local pooling, social LSTM, and then attention mechanisms, things like social attention, SOFI, traffic predict, etc. So one of the downsides, right, of any of these neural net-based approaches, right, is there's, thousands to millions of parameters to learn and a large amount of label data is needed, as everyone obviously already understands. Right. And so, in labeling these data sets is an incredibly time consuming thing. It's this vast manual effort. You either have a heavily instrumented setup or a ton of human effort. And so, again, in trying to figure out our way out of that, Cyrus's work here proposes to use simulation around a small amount of real data to produce a much larger synthetic data set. So the challenge here, again, is to take a small amount of real data, let's say 1 to 5,000 frames, and then use that to produce, through sampling, use that to produce over 20,000 pieces of synthetic data. Okay, so to give you a sampling framework overview, we want to sample the number of pedestrians, we want to sample the trajectories, and that's the path and the speed, and then we want to repeat to simulate the entire data set, right? Okay, what does this look like? Well, we collect individual trajectories, right? So if we look at the data for each unique pedestrian in the data set, then for each trajectory, right, we want to introduce a distribution over other likely trajectories based on perturbation, right? We can think of this like non-parametric kernel densities. Each trajectory defines a density of perturbed trajectories that we're going to sample over, right? So how do we perturb these trajectories in practice, right? Well, you can do small translations in the 2D plane, right? So you can move these trajectories to the left, to the right, up, down, etc., right? And we believe that that is really representative of if the pedestrian had started from a slightly shifted position, right? That the motions that you see there are going to be realistic, but they're going to start from a different set of positions, right? So you can do things like reversal, right? That means if the pedestrian had walked in the opposite direction. So you really can't do that for vehicles, but for pedestrians, obviously that can be very practical, right? They can operate and cross from left side of the road to the right side of the road or vice versa, right? They're very agile and they don't always walk on the road, as we all know. And then finally, we can do things like truncation, right? So we can shorten those trajectories as if they'd started at a different point in time or as if they had gone a different distance, right? So again, right, one trajectory for each unique pedestrian in the data set, sample from the induced distribution of that and perturb at random, right? And then we're going to fit a piecewise linear spline, which has no time information, to give us a path from which we can continue sampling, right? So if we want to think about that, we want to sample speed, right? Each pedestrian is moving at a desired constant speed. Perturbation is normally distributed, and then we sample from a mixture distribution over the different speeds that occur, right? And then we assume the variance is shared. So the ETH data set had 2,000 frames, right? This is from ETH campus and from a hotel. The UCY data set has 4,000 frames from a university. Okay, so the evaluation procedures: pick one data set for testing, the remaining for training, and then repeat this in a cross-field validation approach. For real data, we have about 4,000 to 5,000 frames per training data set, and then we repeat this for all combinations. And one of the things that really jumped out and was really, really powerful here, right, is that we can look at the percentage of real data we use and then test on everything else. And what the measures you see here are average distance error, so lower is better. But the upshot is that, creating these larger synthetic data sets really allowed us to continue to reduce that error when testing, despite the fact that no additional real data was introduced. And this sort of matches up with lots of the work going on in sort of the simulated realm, where we see quite powerful results by taking some real data and combining it with some simulated data. But for the pedestrian domain, we think this is really powerful because this uses something that we know about how people move through the world. So the synthetic data lowers the. So here's some qualitative results. What you see here is with the real data on the top row and the synthetic large data set, which takes some real data and expands it with the synthetic data on the bottom row. And then you can see at t equals 0.8 seconds, 1.6, 2.4, etc. The green line is the observed trajectory, so that's the data we're using to make our prediction from. What we want is we want the predictions in blue to be at the end of the orange trajectory where the pedestrian actually is, right? And positions in all these are where their head is in these locations, right? So over time, the predictions become more scattered, but you can note that the training on the synthetic data is more centered around the real pedestrian as opposed to the real data alone, which you can see diverges more significantly. Here's some other results, right, where we see, again, in this example, training on synthetic data, predictions are more tightly clustered around the pedestrian as opposed to in the real data. Great. Okay, switching gears once again, I'm going to give you one last set of results here from Ming Yuan, who is a graduated PhD student. He's now at Ford. And so he looked at sort of risk assessment and planning with bidirectional reachability for autonomous driving. And so what this is really based on is an intuition that you can see here. So what you're going to see is Ming Yuan driving and he's going to pull up to this area where he actually lacks visibility to the left, and he's going to slow down and sort of creep out a little bit to be able to see left and right and then make that turn. And this is a very intuitive thing that we as human drivers do, but the reality is it's very difficult to build that intuition into autonomous vehicles. So his work was undertaking looking at how do we quantify and understand risk and then use that to produce results like you just saw there. Okay, so I think it's important that we think about ways of evaluating risk systematically for AVs, given any potential move they would make or any intersection they would be crossing or any steering command they're about to execute to understand, what the risk is of some maneuver or something that's going to happen. And we looked at this with a real focus on two things. One is that there's certain actions you can take that are going to be riskier than others. And the second is that you can simulate lots of this, but you can simulate it using the visibility you have of the environment and where potential vehicles could be that you cannot see. And so the real focus here is how do I understand or know what's happening in places that I can't see? And obviously, we don't have a magic wand, but what you can do is make some assumptions. And if you assume that people are behaving reasonably under those assumptions, quantify the risk to your vehicle for any maneuver that you might want to make. So in this example here, you can see that there is the ego vehicle, so us, is that car in blue. And we want to make a left-hand turn here to get to that gold star. And there's a vehicle passing to the intersection when we do that. So what I'm going to show you here is, again, an unprotected left-hand turn. Again, the ego vehicle is in blue. Other vehicles in the scene are in red. The observable polygon is in the transparent green, and everywhere else is obviously not visible given these sensors. The goal we want to get to is that star, and I'm going to show you how we simulate this. And then the baseline is just going to be the car tries to execute the maneuver based on what it can see now. And the proposed approach is to use the fact that we know that vehicles could be coming from places that we cannot see. So I'll pause here. What you see there is in the baseline approach, right? We're trying to make this left-hand turn, and we end up colliding with a vehicle that was coming, but it was coming from outside of our field of view, and we couldn't see it until we got into the intersection. In the proposed approach, right, we're much more cautious because we know that we can't see far enough, and all of those red dots represent potential locations of other vehicles at future time states. So you can see that now, once we believe the intersection is clear, the vehicle executes that turn, but it's based on the fact that its visibility improved as it moved further into the intersection as opposed to from where it was before. And you can see that this differs for a variety of different intersection geometries and types. And so one of the critical things that we think is important here is that you can understand a lot about the intersections you're going to be going into just from the geometry of those intersections without having to actually be in them. And so all this simulation work can be done a priori, and you can look at whole environments and understand, okay, well, the visibility in these scenarios is bad, so I should be doing something different. More importantly than that, you can simulate a variety of different sensor locations, fields of view of your sensors, and understand, how safe or how risky is this configuration or this intersection, again, before you do anything. Right? So the way we actually go about doing this in practice is we use forward reachability as our metric for understanding, what we think the risk is of an environment, right? So we can use the system dynamics of the vehicle, and that allows us to produce a forward reachable set that says in the next, parameterized with time, in these many seconds, these are the possible locations my vehicle could be in. But the power of that is we don't have to use it for just the ego vehicle. We can also do it for other vehicles in the scene or other vehicles we can't even see. And so you can use the fact that you can't see in a place and produce a forward reachable set in the worst case scenario as if a car was there and determine, where there would be potential collisions moving forward. Right. So in this example we showed earlier in the presentation, right, we want to make this left-hand turn with the blue vehicle to the yellow star. And we look at the forward reachable set of both the blue vehicle and that red vehicle we can see, and we see that those don't intersect. So there's no overlap of those predictions. And so we know for the next n seconds, as far out as that forward reachable set predicts, we believe that we are safe to make that maneuver. Now, there's a hypothetical vehicle that could be in that location where we can't see. And so this encourages our vehicle to move up to increase its visibility until it gets to a point that if all the other cars are obeying the rules of the road, we can ensure that there isn't a collision. And ultimately what this is trying to move towards is the fact that, given our current visibility, we can understand how much risk are we incurring by executing any maneuver. So if we were to pull in that intersection, we know that if a car was going 30 miles an hour and it was in the position of either of those cars with the red forward reachable sets and the question mark on them, only the car on the right would cause a collision. And so we can do this again at a macro level for all of the potential cars that could be in that intersection. And then we can do it for all the intersections that exist that we see around in any given environment. In fact, we did this for the context of Ann Arbor. We pulled all of the pre-existing map data and looked at that map data and then quantified the risk of any collisions in any of those intersections. And that we think at a global level, this gives you the ability to decide routing or make decisions based on what you think the risk is to your vehicle, or even think about different vehicles in a fleet where all the vehicles are not the same or all the sensor configurations are not the same, and make decisions about routing large numbers of autonomous vehicles without having to put people at risk. Great. I'll stop there and take any questions.